So last time we talked about implicit memory allocators. And we looked at the implicit list and specifically how we can keep track of, we can keep track of allocated and free blocks. So today, we're going to look at some more complicated solutions like explicit lists, but that hopefully can give us better performance. And by performance, I mean both throughput and memory utilization. So last time we looked at this algorithm when we have to iterate through the entire heap. So from start to end, then we looked at the condition that the corresponding memory block is not allocated. So that's the first condition that we want to make sure. And its length is like at least of the length that we are looking for. If either of this condition is not true, then we have to move on and go to the next block. So that's the idea, right? And remember, this -2 means this mask when we throw away the lowest bit. Okay. So how do we allocate a free block? Well, the idea is that we're gonna be splitting, right? So we're gonna find the block. Let's say let's say this block is larger than what we are looking for. So we might want to split the block. So for example, we have block 24 of size 24, and that's what we're gonna use, right? So and now we want to split it into two pieces. One is going to be 16 bytes, and the remaining part is going to be 8 bytes. So okay, so one thing that to note here. So when you're gonna do that, sometimes it's possible that when you split a free block, you just have like 4 bytes left, right? When in this case, like a word size, right? In your case, when you're going to be implementing your own memory allocator, it's going to be 8 bytes because word size is 8 bytes. So yeah, so it's not worthwhile to create a free block at that point, right? Because you cannot basically allocate anything inside. You can just allocate an empty header. So in this case, you can use it as some sort of trailing piece of the allocated block. So when you do splitting, just make sure it's worthwhile to do splitting. If you just have barely any space left just for a header, yes, that's probably you don't need to split it. Just allocate slightly more, like 4 bytes more or 8 bytes more in your case, and that's it. Okay, so how do we split? So we have this P location, right? And then we want to have size. So size in our case, 16 bytes. So first of all, we want to round up, to even size. So recall that we are using the lowest bit, right? So we're using the lowest bit, so we have to so we have to throw away the lowest bit. So, but we have to round up, not round down. So you have to, it's okay to allocate slightly more, but not less. So to be honest, once you're gonna start working, rounding up is not sufficient, right? So you actually have to probably align it. So it's not just rounding up. But for a moment, let's just assume that we can round up. So we have length, and let's say just for the sake of this example, it was not, well, it was 16, that's fine. Let's take 16 first. 16 plus 1 shifted by 1. What is this? So this is 17 shifted by 1. Any ideas? Oh, by the way, why don't we have too many people today? Is it because of career fair or what? Okay. So 17 shifted by 1. So what is right shifted by 1? So that's divided by 2, right? So 17 divide, well, roughly divide, unless we are dealing with negative numbers, but that's we are not dealing with negative numbers. I mean, even with negative numbers, it's divided by 2, but the question is where you're going around, to which direction. So 17 divided by 2 in integer division, that's going to be what, 8. So, and then you and then you left shift it by 1. So that's basically multiplied by 2. So now you get 16, right? So rounding up, 16 is still 16, right? So, but now let's try. So we are not allocating anything extra, even though we added 1 initially, that was thrown away. So now if we add 15, let's say it was 15, then we get 16 shifted, right shifted by 1 is going to be still 8, and left shifted by 1, that's going to be 16. So 15 will be rounded up to 16. So does it make sense? Yeah, so this is how you can round up. Okay, go ahead. Well, you can also add, well, it depends, right? So if you can use a mask when you wanna, when it's going to be a power of 2, right? So if you want to throw away the lowest bits, right? So what do you mean by mask, right? So oh yeah, so what you're saying, well, but we remember we have to add 1 still. We have to round up, not round down. Or you mean that we can add 1 and then a mask, right? Okay, that's true, right? So that's okay. Yeah, so that we can do. Yeah, it's okay. So we can change this to shift operation to 1 mask. Yeah, you're right. Yeah, so but you know, one thing I mentioned, shifting rounding up is not sufficient, most likely. You will have to find the line size, most likely, right? So in your case, I mean, is it 8 byte or 16 byte aligned? You have to find that size, right? So it's not just rounding up to the even number, right? But to the multiple of 8 or 16. Yeah, so yeah, that will be also relatively simple, but just letting you know, like for a time being, let's just round up, right? So because we need to clean up the lowest bit, so that's the main thing that we worry about, right? So because we need the lowest bit for something else, so this is why we want to have an even number. So now old size is what? So this is P, and then we have to throw away the lowest bit, right? So we dereference P and throw away the lowest bit. So this is mask with -2. So now, well, the new block will definitely be marked as allocated, right? So you have new size bitwise OR, right? So and then 1. And then you check, okay, new size is less than old size. Okay, so is it less? Yeah, if it's not less, then you know we are done, right? But if it's less, then we're gonna mark the remaining region as free block. So now again, it's not just probably less than old size. If it's just 4 bytes left, you don't want to use it. Okay. Is everything fine? Just okay, go on.
I assume that we would have had to do a check earlier to make sure that like new size isn't greater than old size.
New size isn't greater. Where do you want to do this check?
Well, like if you're trying to allocate a block of memory that's more than 24 bytes.
Well, yeah, certainly, right? So, but that we already ruled out in the beginning, right? So, because when we were looking for this block, we found this block that satisfies the condition that it's, you know, so it's at least of the same size, right? But now we are just considering a case when it's larger than the requested size, which is not uncommon. So this is, oh, in the battery, I have to replace the battery. Just give me 1 second. Okay, so by the way, in the previous slide, why we didn't set any bit when we had this free block? I mean, we just initialized size. Well, because the bid is 0, right? So there is no, so it's basically there's no need to set anything for a free block. We only need to set it for the allocated block. So the lowest bid should be set to 1 for the allocated block. For a free block, it's going to be the same as size, right? So there is no need to set any extra bits. Okay. So what is next? Okay. How do we a free block, right? How do we want a free block? So let's say we want to call this, right? So and then just the simplest way is like we just gonna go and clear the bit, right? So we're gonna go and just say, okay, now this header is no longer allocated, right? So you're gonna change size and mask out this lowest bit. But if we just do that, we will have some sort of false fragmentation, right? So now if we attempt to allocate, do malloc 20 bytes, even though we have the 20 bytes, it's not going to allocate anything because we will have two adjacent free blocks which are not merged together, right? So that's a problem, right? So we need to do something about it. So there is enough free space, but the allocator won't be able to find it. So what can we do? We can call less, right? So we can join with the next or previous blocks if they're free. So how do we do that? Well, one thing that is clear is that we know where the next block is. So when we deallocate the current block, we know where to find the next block. So we just go there and check, okay, is it free? Okay, it's free. Let me just increase my current scatter size by the size of that free block that is adjacent to me. So like from a block 16, I can get to block 8, right? So we have a block of size 8. So now I see, okay, the next block is also free. So let me just change my current size to 24. And that means, I don't even need to care about the old header. I can just, it's already logically done, right? So I don't need to worry about this because the header size has just increased. Okay, so the free block, what are we gonna do? We're gonna mask out the, we're gonna mask out the allocated free bit, find the next block, and then, okay, if it's not allocated, we're going to just increase the size of this, our new free block, right? So this is how we're gonna join them together. So yeah, it looks like we have solved the problem that we had, but it doesn't fully solve the problem. Because how do we call less with the previous block? Any ideas? Any ideas? Yeah, so I mean, how do we call less? Because I know how to go forward, but we don't know how to move backward. Because I don't know what block size in front of me, right? So how do I know how large the block in front of me? Okay, go ahead. Well, but we don't have a linked list yet. Remember, that's not a linked list. I mean, it's implicit list, right? So there is no explicit pointers right now. We'll get to the explicit list when we actually keep free blocks in a list. But right now, the only thing that we are doing, we are scanning the heap. We are jumping from one block to another block, just using size, right? Not anything else. So we are not keeping any explicit pointers. So we just start from the heap, we have size, we added size for the first block, we go to the second block, we add another size, we get to the third block and so on. So we are not keeping any pointers yet. Well, it turns out there is a very simple solution to this. So let's just use a footer, in addition to header. So this is also known as boundary tag. So we'll replicate size and allocated word. So at the bottom, at the end of three blocks. So that way we will be able to traverse backwards. So I say free blocks. We'll get. Let's just assume for a moment that for all blocks, we'll get to this optimizations later, right? So what we can do about the footer to make it more efficient. But just for a moment, assume that we can just replicate footer and put it in as an addition to the header. So effectively, your payload is now a sandwich between header and footer. So this way we'll be able to traverse backwards. So how we will traverse backwards? Well, now I know that the preceding, just before the header, I have a footer for the previous block. So in that way, I know the size of the previous block. And I also know whether it's allocated or free because I also replicate that bit as well. So in case if I find that it's a free block, I can also coalesce with the previous block. So the idea is very simple, right? So just replicate the size. So now let's say we have a case one, a block that is going to be freed. Okay, so it's surrounded by allocated block. Okay, then we are done, right? So we just free this block and that's it. So the case two, the next block is also free. Then I am going to coalesce with that next block. Okay, the third case is that the next block is allocated, but the previous one is free. So then I'm going to coalesce with the previous one. And finally, both the previous and next are also free. So I have to coalesce with both of them. So, and then my new large block is going to be shifted to the previous block. That's going to be a large free block. So by the way, do we only need to care about previous and next blocks, or do we need to care about anything else, like any following block? What if the block after the next block is also free? Or the block before previous is also free? Is it possible? No, it's not possible as long as we always coalesce, right? Yeah, so that means we will always have just one, at most one block on the left and at most one block on the right. So in that case, it's really kind of constant time coalescing because I really know that it's not going to be more than two operations effectively. So we have this, right? Now we don't do anything. Then we have case two. So that becomes a larger free block. So we effectively erase the next header, and that becomes a large free block. So not large previous block and large entire space, right? So that's going to be also placed in the previous block. So that size is going to be updated in the previous. Don't forget in the last case, or as well as in case 3, that's going to be previous size, not the current size. So does make sense? Yeah, so yeah, this is how we can avoid this false fragmentation, and this is how we can also implement the free operation. So now, what are the disadvantages of boundary tags? Well, recall that we mentioned internal fragmentation. So one thing that we have external fragmentation, we want to avoid this, and especially if it's false external fragmentation. But another thing is internal fragmentation. So now, in addition to header, we also have footer. So I have a large overhead. So now I have to keep more stuff. So yeah, but it turns out there is some solution to this. So I guess once you start implementing your project, and let's say you're gonna implement some good algorithm like segregated list, so that means you have multiple lists, you'll find that you still don't have highest memory utilization. So maybe you are kind of have a high memory usage, but not as high as you want. So it may be like 90%, 95, I don't know, sometime somewhere in that range, depending on what you implement. But not 100%. So at that point, you'll need to do something with the footer. All right, so you will need to somehow get rid of the footer, but you cannot get rid of it completely, because if you get rid of it, then it causes other problems, right? So it turns out there is a nice trick that you can use, which I'm going to probably talk about that trick later, right? So I don't want to put too much information right now. So I guess you'll probably first try to implement your whatever you think is right, and then maybe I'm going to give some hint how to solve that problem. So once you reach this 90% score, yeah, so yeah, it shouldn't be hard optimization once you are done. Okay. So let's just summarize the key allocator policies, right? So the placement policies is the first fit, next fit, best fit. You know, we may trade off low throughput for less fragmentation, you know, but one interesting observation, and that's something that you will also find when you keep multiple lists, like segregated lists, so that means you will have multiple explicit lists, is going to basically take both of best world, right? So it's going to have like sort of best fit, because you're going to find, well, it's not entirely best fit, but an approximation of best fit. Also, it doesn't require to go through the entire list. So you're gonna have multiple lists, and you kind of get both throughput and less fragmentation, right? So this is why segregated list is most likely the approach that you want to use for the project if you want to get a high score, right? So I mean, again, don't start with the segregated list right away. I would at least start with the explicit list first, and then make sure it works, and then I would expand it to segregated list. Because again, segregated list is nothing more than just multiple explicit lists. So okay, so what is this? What is the splitting points? So how can we go ahead and split three blocks? How much internal fragmentation are we willing to tolerate? You know, so those are the splitting policies. So now coalescent policy is also something that we can for which we have some different implementations. I mentioned constant time coalescing when we immediately coalesce with our neighbors. So that means immediate coalescence. Coalesce each time 3 is called. So that way you're always guaranteed to just look at your neighbors, right? So you're always guaranteed that only the next one is at most free, and maybe the previous one is free. But there is also a possibility to have some deferred coalescing. So you can kind of try to improve performance of free by deferring coalescing until it's needed. So for example, you can coalesce as you scan for memory in malloc. So you can realize, oh, there is free neighboring block, let me coalesce them. So that's how you can also do that. I mean, that said, I wouldn't probably recommend that, but you know, certainly it can be done. So, or when the amount of external fragmentation reaches some threshold, you can say, oh, let me scan the entire heap to see what I can do about it. Yeah, so that's also a possibility. So whether it's a good approach, whether it have a deferred coalescing, I think it's kind of debatable. So, you know, after all, immediate coalescing is also not that expensive because it's constant time. But of course, you have to look at two blocks that, you know, you may argue that if And depending on application, if it's not likely that they are free, then you're kind of wasting some CPU cycles for doing it. So in terms of the implementation, implicit lists are very simple. So in terms of allocate cost, sorry. So in terms of allocation cost, it's a linear time worst case. So the worst case scenario, I have to go for the entire heap and to find the right block. So free cost, const time in the worst case, because the only thing I need to do is to mark the block as free, and also I need to coalesce, right? And coalescing is constant time because I at most need to coalesce with the previous and the next block. So the free is constant time. So memory usage. Well, that will depend on the placement policy, and this is where you can potentially have not so good memory utilization because especially if you use first speed, you can have a lot of external fragmentation. So that may not be that great. So one thing to keep in mind that it's not used in practice for malloc free because of linear time allocation. I mean, linear time allocation is pretty bad, right? So what if I need to scan the heap of like several gigabytes, right? Or maybe that's a lot of memory, right? And that I can waste a lot of time for just one malloc call. And especially if I have a lot of malloc calls that can, degrade performance significantly. But it can still be used in special purpose applications. I mean, you don't necessarily need complicated allocators all the time. But for your project, you get a high point, you need something more complicated than this. I mean, again, it will probably be okay for a checkpoint. So in case if you're running out of time for checkpoint, at least implement an implicit allocator. But otherwise, just try to go with the explicit allocator right away so that you don't. I mean, because otherwise, what may happen, you submit checkpoint, you're happy, right? But then the final deadline is coming up, and that means like you have to re-implement everything from scratch. So it's better to start working on this early. But sometimes I know that from my experience with explicit list, people can get stuck because of some bugs. So there is still some bugs in the list, and so they're running out of time before the checkpoint, and so then at that point it's okay to implement an implicit list at least. Okay. So, but the concepts of splitting and boundary track coalescing, are general to all allocators. So that's even though we describe it for implicit list, it's still relevant for explicit lists. So now let's look at the second method, explicit list. So when we explicitly keep track of free blocks. So in the explicit list, fundamentally, we need to keep track of free blocks, and we just need to effectively insert pointers. And let's create a double linked list. So why would it be necessary to create a double linked list? Any idea? Why we cannot just use a single linked list? So what is the advantage of double linked list? I mean, other than we can iterate in two directions, what is the main advantage of double linked list? Just any guesses? I mean, what we can do with double linked list, which we cannot do with a single list. There's one thing that we can do with double linked list. Well, what we can do, if I have a block, just a node, right? Whatever it is in the list, I can always delete it. and I can always delete it in constant time. So I can just go to the previous node, update its next pointer to the node after me, and I go to the next node and update its previous node to the node that precedes me. So I can use, so effectively we can have constant time, right, for deletion from that list. And that's useful because we still want to keep free constant time, right? So we don't want to make it linear. So this is the major advantage of a double linked list. So with single linked list, we can go to the next node, but we cannot update the previous node. So we cannot just, we have to find we have to locate the previous node. And I don't know where the previous node is unless I start scanning from the very beginning. So I can go to the next node, but I cannot go to the previous node. But I need to update the previous node's next pointer so that it will skip my node and will point to the next one. Okay, so we're gonna keep next and previous. So this is, so by the way, maybe so far when you dealt with lists, you would have to kind of allocated nodes explicitly. So this is something different here. So we look, we don't actually allocate any special place for this list or for the nodes of the list. So when the block is allocated, there is no point to keep track. I mean, there is no list of allocated blocks. So there is no need to keep next and previous pointer. So when the block is free, the payload area can be recycled to keep the next and previous pointers. So, so in other words, when we allocate for allocated blocks, we are not wasting any memory. And for free blocks, anyway, we have free space. So why wouldn't we keep a next and previous pointer in this free space? Any question? Example, okay. Okay, okay, so what do we have, right? So we have, let's say we have header, and this is payload, right? And this is footer. So let's say it's unallocated block, right? So this is marked allocated 1 in the header and in the footer. So now I'm going to free this one. So currently, this is the useful data, right? So this is something that the user is using. So let's for a moment assume that the payload area is at least like greater or equals than 8 bytes for 32-bit CPU or 16 bytes for 64-bit CPU, right? So that we can at least give 2 pointers there. So now we want to free it. So what we're going to do, we're going to have header, footer, and then there is a free space here. So there is a free space to at least feed 2 pointers. Maybe more, I don't care if I have more space. But at least there's like 4 bytes here, 4 bytes here. Well, in case of 64-bit CPU, you have 8 bytes here and 8 bytes here. So now you want to keep this as previous and as next. Remember that the free block doesn't care what was before that. The free block can erase the payload. So once the block is free, you no longer need the payload area. So you recycle that area to previous and next pointer. Does it make sense? Okay.
If we don't have any pointers inside the block itself, how would we know to get to it in the first place?
if you don't have blocks, well, what do you mean?
Like in the allocated block.
In allocated block, but allocated block should not be added to the list. So remember that next time we only care about free list. So only free blocks have to be connected. Allocated blocks are kind of blocks that are kind of stranded somewhere else, right? So they're currently allocated, we cannot use them.
And we just trust the user program to handle them.
Well, because anyway, we have to trust the user program. User program can always corrupt the heap, right? So in this case, because we are only this program is using this particular heap, only this process, right? If the process corrupts its own heap by doing something wrong to memory, that's the problem of this process, right? The OS will not be corrupted, or the other process will not be corrupted, because they will get to that point when we have the virtual address space, right? So only this particular process, this memory allocate is used just for this particular process. So that's our assumption. So does it make sense? So only free blocks need to be kept track of, right? So we don't care about allocated blocks. They are already allocated, we cannot touch them. Okay, is it okay if I just keep it for a moment? Because if maybe I will still need to use a Blackboard, right? So is it okay if I just keep to this like two projectors? Okay. Okay, so what do we do? All right, so the next free block, so can be anywhere, right? So if you don't actually need, so at this point, this is different, right? So in previous case, we would go from one block to another, right? So to the next that resides in memory, right? So to the adjacent block in memory. Now the next here or previous here can be anywhere, right? So it doesn't have to be the adjacent or the closest free block, whatever, right? It can be anything. So just remember that it can be anything, right? So because we are going to keep track of free blocks differently. So this is why we have these pointers, because sizes are no longer sufficient. We can have forward and backward pointers. So we still need boundary tags for coalescing. So what does that mean? Well, you probably, let's kind of put it off for a moment. But if there is some adjacent block which we can coalesce with, we want to take advantage of this, just like with the implicit allocator. So now that means I may potentially need to delete an adjacent free block from the free list when I'm doing coalescing, but we will look at that, right? So there might be some additional operations. So this is why you may need to have an ability to remove a free block from anywhere in the list. So this is exactly why we actually need it, because for coalescing, that's going to be really useful. Okay, so logically, it looks like this nice list A, B, and C, right? So this is how we look at this list. But physically in the heap, it can be any order. It just can be completely random order. So it depends when we allocated free blocks. Whatever was whatever order we were allocated in free blocks, right? So this is really completely random. So just keep that in mind. So this is again not necessarily the closest free block, just any free block. But one thing to keep in mind that the free block can only appear once in the list. That's for sure. So no matter how it's ordered in this list, it can only appear once. Okay, maybe I can still use that. Okay, so let's say how we allocate from explicit free list. So initially, let's assume we have two like we have a list of free blocks, right? So now we found this free block in the middle that satisfy our request, that we found that it's at the very least of the size that we are looking for. You know, the preceding block perhaps was not of the same size, but this one is of this size. So what do we do at this point? Well, we have to split this block. So we have to exclude this free block from this list, take it away, then split it into two pieces. One is going to be allocated piece, and then the other is going to be free piece. And then this free piece has to be inserted back to the list, right, to the original free list. So whether you're going to insert it to the same place or to a different place, that's a different story. I think that may give different performance, right? So, and I guess with segregated list, you need to be careful because you have to order, right? So once you split it, you know, so that block can be of completely different size and may end up in a different list altogether, right? So, but you want to make sure that you excluded the original free block. That's important because now this block is going to be marked as allocated. And then the remaining piece you're going to insert back to the free list. So whether you're inserting to the same location or just to a new location, that doesn't matter too much. Well, it may again matter depending on the policy, but fundamentally from the correctness standpoint, doesn't matter. So free in with explicit free list, right? So in general, we're gonna put a newly freed block. Well, there is a different policies again that you can take. So one is LIFO, last in, first out. So insert free block at the beginning of the free list. Just insert it to the front, and that's it, right? You can also insert to the tail of FIFO, right? So if you keep track of tail pointer, but that's just a variation of the same thing. So the pros is simple and constant time, right? So it's just like really just one operation to insert to the front of the list. But you know, some studies suggest that you know fragmentation can be worse, right? So then when you do some address ordering. So now sometimes, as I said previously, you don't have to put the closest, but maybe sometimes you want to put the closest pre block as the next block, right? So if you choose that policy, then you can do that, but that will require search often, right? So that's going to be a linear search now. So it's no longer constant time. But fragmentation can be lower. So that's the advantage. So I guess if you use something more complicated, such as segregated list, probably you won't need to worry about this too much because I don't think there will be a significant difference between either of these two approaches once you use the segregated list. So maybe you want to just go with the simplest one. But if you just use a single explicit list, then it probably matters because all free blocks are in one free list. And whatever policy you're using is going to actually affect performance significantly. So how do you free a block, right, with a LIFO policy? Well, let's say we have this free, right, and then we decided, so maybe the neighboring nodes are already allocated, so they're also marked as allocated, but now I'm freeing block and have to insert it to a free list. So now the root of the list, so the pointer is going to get updated, right? So now the root is going to point to the free list. So the first pointer, the start of the list will point to the new node, and the new node next will point to the node that root was previously pointing to. And then you also have to update the previous pointer of that node, of the node that was previously first. So the node that was previously first will become the second node, and your freed node will be the new first node. So that's fairly straightforward. So in this case, you don't need to do any coalescing because neighboring nodes are allocated. So let's look at the second case. When you free a node, but then the neighboring node, the next node is also free. So what are you gonna do in this case? So you already see that this neighboring node somewhere in the middle of that list. Not necessarily in front, maybe it's in front of the list, I don't know for sure, right? So, but it's somewhere in the list because there is no guarantee of any order. So what are you gonna do first? You wanna exclude the neighboring node from the list. So you wanna remove it from the free list. Then you're gonna coalesce, and then you're gonna insert like larger new node to the front of the list, just like previously. So don't forget to remove the coalesce, the node that you're going to coalesce with from the existing list. So with double linked list, it's easy to do that because you can always go to the previous and next node and update their pointers. So once you remove it from the list, you can coalesce with this free block. And the larger block will get to the front of the free list. So does it make sense? There are multiple operations here. So you have to remove that block from first. Don't forget that. And remember, that can be anywhere in the list. You don't know where the neighboring node is. Cannot make any assumptions about that. I see some confused faces. So any questions? Yeah, so again, look, we have this free block that we are trying to free. So this is we are about to insert it to the front, just like in the previous case. But before we do that, we need to make it larger. We need to coalesce with the next block. But the next block is already free. So that means if it's free, that has to be somewhere in the list. We don't know where exactly it's in the list, but it's somewhere in the list. So our goal is to remove that free the neighboring node from the list. And we can do that with the double linked list easily. So once we have done it, we can coalesce and the new block will be inserted to the front. New larger block will be inserted to the front. So case free is very similar, but just for the previous block. So that's the same idea. So now this case is tricky, right? So when the case 4, when you have to coalesce with 2 neighboring blocks, you have to make sure you remove 2 of them, right? So you remove previous block from the free list, you remove the next block from the free list, and then you merge it together with the current block. And then larger block, you insert it to the front of the list. So now you see that in this larger block is not appearing right in the next or like in the previous neighbors of the of your, I mean, it doesn't appear in the previous list, right? So this is why it's important to because you may use different strategies, but the right strategy I think would be first remove that neighboring node from the list so that it's no longer in the free list, whether it's predecessor or successor, right? So make sure you remove it if it's marked as free. Then coalesce and then insert the larger block to the front. Don't look back to the whatever was previously there, right? So if you look at that, it can easily get confused. So just update those pointers, exclude it from the list first, and then insert the larger block to the front. Because anyway, the size of the block changes, so there is no, I mean, whatever the policy you're using probably is not gonna be, you're probably gonna insert it to the different place anyway. So does it make sense? Any questions so far about it? Okay, go ahead.
You say splice out predecessor successor blocks. Do you set those to how do you do that? you set that goes current where it is currently, or you just take it out of the list of vacant property?
Well, you know where your neighbors are, predecessor and successor, right? So because you know that from the size, right? You still have header and footer, so you can always get to them, right? From header and footer. So now, once you got there and you saw that, okay, it's a free block. So, and that means you can coalesce with the current block, right? So the first step that you're gonna do, remove it, because remember that any free block must be in the free list. That's our assumption. So we have to exclude it from the free list first. So how do we do that? We go to this neighboring node, go to this, then it has a previous and next pointer. I have to go to the previous, update pointer so that it will skip that node, and I have to go to next, update its also. So just a standard right removal operation in double linked list. So this is why we are using double linked list, because you don't care about the position of this node. You can always remove it, right? So it's a constant time removal. So you remove that neighbors from their free list if they are free, coalesce and insert a larger block to the free list, to the front of the free list. But make sure you do that, because otherwise, sometimes I saw a lot of bugs in the past when people were trying to, forget to remove it, then a lot of, weird things will happen. So imagine if you forgot to remove it from free list, and then it's kind of piece of another block, which also appears in the free list. All kind of crazy things may happen after this, right? So you have to be careful when you do this, right? So I actually recommend you to when you write your code to check it, right? So it's better to spend more time while you're coding, and then just spend less time debugging it, as opposed to kind of writing very quickly some sloppy code and then spending hours and hours to debug it, right? So it's better to spend more time just checking, double checking, triple checking, right? And then, hopefully just debugging minor issues after this. Because this is the place where sometimes it will be hard to debug, because by the time anything happens, it's already too late. Your entire heap is corrupted and you don't know the point when it was corrupted. Maybe it was corrupted long time ago and you just see it just manifests only right now, right? So it sometimes can be really tricky to catch these bugs. So my strategy is to also review your own code and look at this from the like critical standpoint, question every line that you wrote, right? Okay, so how do we compare explicit list to implicit list? So allocate is linear time in terms of free blocks instead of all blocks. That's important, right? So now we don't need to scan all blocks. Like as your heap becomes more and more filled up, there is no point in looking at allocated blocks. So you want to just look at the free blocks. So it's going to be much faster when most memory is full. And when memory is not full, perhaps you're going to be finding free blocks faster anyway, right? So it's slightly more complicated to allocate and free, since we need to the splice block and in and out of the list, so we have to deal with this explicit list now. So this is an extra operation. So in addition to coalescing, we have to deal with that explicit list, and have to update next and previous pointers. So this is also some extra space for links. So we have to have 2 extra words for each block. Does it increase internal fragmentation? Well, that's a tricky question. On the one hand, it doesn't, because we don't waste the space for allocated blocks. But it may also indirectly matter, because now if I have to split some block when I'm allocating, let's say I'm allocating 20 bytes, and I have 24 bytes block. Oh, sorry, I have 28 byte blocks. 24, that wouldn't make sense. I would just, I just would allocate 24 because there is no point to create just a header for a free block. But now if it's 28, yeah, I can only put header and footer. So let's say not 28, like I have 32, right? So now I have header, footer, and maybe 4 bytes for the payload. But now I still cannot do that because I at least have to have 4 more bytes to have a free block. So I have to have at least 36 bytes rather than 32. So it can potentially increase external or internal fragmentation because free blocks have to be larger now, right? So the minimum requirement for free blocks is at least that they can hold 2 pointers and header and footer. I mean, there is ways to you can optimize it, but it still can potentially increase fragmentation. Yeah, so also most common use of this linked list is in conjunction with a segregated list, segregated free list. So we're gonna keep multiple linked lists of different sizes and possibly even different types of objects. So let me just give you a very brief introduction to segregated list before we wrap up. So what you can do, you can create each size class of blocks of its own free list, right? So you can say, okay, if it's 1 to 2 bytes, well, probably not 1 to 2 bytes, probably at least 1 to 2 words, use that list, free words, different list, and so on, right? And you create different classes, and now you have a lot of different explicit lists. One strategy that you can do, because you can have too many lists, right? And how do you decide which classes you have to use? One strategy you can use for your project is to use power of 2 buckets, right? So like you can have, let's say 8 bytes, 16 bytes, 32 bytes, 64 bytes. So that means that's the largest size that you have in that list, right? So that means if I have 8-byte class, I have from 0 to 8 bytes, including if I have 16 bytes, it's going to be 9 to 16 bytes. Then if I have 32-byte class, it's going to be 17 to 32 bytes, and so on, right? That way, how many buckets you will need at most? So how much memory you have? 2 to the power of 64. Well, you have actually less than this memory, but like the worst case scenario, right? In the 64-bit processor. So log 2, if you have power of 2, log 2 of 2 to the power of 64, that's just 64. So you're going to have at most 64 lists, actually less than this, because you're probably not going to be keeping very small lists, and maybe very large lists are also not necessary because they're not even supported right now, like this memory sizes. But so even if I have to keep 64 lists, that's just a constant, right? So that's a reasonable constant, and still the approach that I have described is reasonable: 8, 16, 32, 64, 128. So that still kind of allows you to group different blocks in different lists. And especially for smaller blocks, you have many more classes, right? Which is actually very useful. Because if it's a large block, probably at that point you don't worry too much. But for smaller blocks, you may need more precision. So this is actually gonna work very well, right? And you can also get the location of that of the list based on the size. So if you find log 2, you will be able to locate where this list is. So you have an array of explicit lists effectively.